Alright, so I did my project on materials for different ores. So boats, before steam power, there were only a few ways to move them. Poling by sail or by oar. And oars gave the most control out of those three ways. And that was understood by ancient civilizations. And in 1900, rowing became an Olympic sport. So the quest to perfect the oar really began. So mechanically speaking, an oar is just a beam that's loaded and bending. It has to be strong enough to carry the moment exerted by the oarsman without breaking. And it must have a stiffness to match the rower's own characteristics and give them the right feel. And very important, it must be as light as possible. An additional constraint is that it has to have a high enough toughness, because oars, they run into things, they get dropped, and if their toughness isn't high enough, they'll just break. So our constraints will be a specified length, a specified stiffness, and a toughness greater than 1 kilojoule per meter squared. Our objective would be to minimize the mass, and a secondary objective would be to minimize the cost. So our selection. So this is the Young's modulus plotted against the density, which is the material indice. The slope of the line is 2, and it's positioned in a way so that the materials above it are the best selections. So our materials above the line are woods, carbon fiber reinforced polymers, and certain ceramics. So those are our 3 best selections. Of those 3, the ceramics are too brittle, their toughness isn't high enough, so they aren't a suitable material for an ore. That leaves wood and carbon fiber reinforced polymers. And of the 2, the carbon reinforced polymers are better. They're just as cheap as wood, and they give more freedom when creating an ore. So our objective, make the best ore with the lowest mass. We selected our carbon fiber reinforced polymers. Our rationale is that they're better than wood, and they're just as cheap. And our concluding remarks is that the ore can likely still be improved, and they are testing different materials and trying to figure out new ways to make them. So it's not a solved game. It's not, this is the best way to do it. But for now, this is what we've come up with. If it wasn't carbon fiber, I'd definitely choose wood. I might choose wood just in general, because if you're not competing, wood has the authentic feel to it. You know, it's been being used for centuries. And as someone who played baseball, like just wood in general, like it's never going to be the best, but it just has this like nice feel to it.
Hello everybody, my name is Kevin Colley, as you can see, and today's materials for table legs and auxiliary. Obviously the problem description is that a designer wanted to make the thinnest legs they can, and then as you can see the 3 variables are both choice of material and diameter of legs. Obviously you want to minimize cost depending on who you're selling to, I guess. I mean, it really is, like I said, who you're selling to. The main constraint would be the diameter. And then here's all the material index basing off the buckling constraint. We've seen a lot of this in our class, but then you get your buckling material index. And then just for your material index for your thin leg, it's just directly proportional to your elastic modulus, or Young's modulus, you know. And then here are the 3 best options at the bottom here. You got your CFRP, your wood, and your butt. And then obviously here's the charts. You can see this is from the case study explicitly. They went with an elastic modulus of 100, probably based off of the weight of the glass and whatever would be on the table. But as you can see, this pretty much leaves it to wood, to CFRP, or to ceramics. But and then your good choices of that. And then obviously throw a little comedy in there. Expensive but extremely thin would be diamond and tungsten carbide. And then obviously, yes. So in summary, the design objective is to minimize cost and thickness. And then I selected CFRP, or carbon fiber, for pretty much a layman term. I figured, honestly, it's kind of funny to have a carbon fiber piece of furniture. That's just me. If you've ever seen it before, it's just pretty. As you can see here, it's on the left. And then the rationale behind that is that it will have extremely thin legs and be light. and then has a certain feng shui in the room. And then concluding remarks would be selection is based on the wanted diameter. If you want a thick leg, you can almost get away with a foam if you really expect it. And then, as we can learn with this, material selection has applications in interior decoration.
Hi, my name is Bryson Clifford. My project was to go over the cost of structural materials for buildings. So I included 2 photos. One was of the aqueducts, the Roman aqueducts, and also the steel truss bridge, which both are good examples of common building materials. So the design problem, just a quick introduction. The material costs account for roughly half the cost of a building. So whether you're buying a house or you're building your own home, the materials cost the most, and that's just because they're used in such large quantities. So materials are used in 3 ways, either for the structure, for support, for cladding, which is like the exterior for environmental protection, and then or as internals, which would be like internal dampening of sound or insulation of heat. So either way, you want these to be safe and you want them to be as cheap as possible. So my case study was to specifically look at the floor joists or just floor beams. So for the model description, you can actually model this as a simple beam with 2 supports. So the constraints, you want it to be stiff and you want it to be strong with a specified length and load. And then of course the cross-sectional area was given in terms of D and B, and then Y sub M is measured from the neutral axis to the top of the fibers. So that is an important part when you're substituting in. You have to make sure that all of these are in terms of area, and when you substitute into your constraint equations, you put that in the cost, and you'll get your performance equations, which give you your material indices, like we've done in class. So from that, you can create your charts. You have a stiffness chart and a strength chart. So you're going to use the guideline for minimum cost, which ours ended up being the middle one. So you just move it over to the top left since you want a material that has the highest material index. So if you compare the values, you're going to see that concrete and brick are best in stiffness. And then as far as strength goes, stone, cast iron, woods, and steels are all better in strength. So a key takeaway from this was that actually concrete, brick, and stone are only good in compression. So it's important depending on the application of them. And then the other 3, wood, steel, and cast iron, are actually good in compression and tension. So that makes sense. You know, the Roman aqueduct picture that I showed is made out of stone, and it's just got its own weight holding it together. And then for, you know, compression and tension, steel is perfect for bridges and things that need to be able to sway and give with loads. So in summary, my design objective was to minimize cost of floor joists. The material selected, the cheapest option was actually concrete, but since it's not great in tension and it's really heavy, I would not recommend that as beams in your house. So I would recommend wood or steel. Wood would be best for residential homes since it's not going to be under a lot of foot traffic and won't have huge loads. And then of course steel will be better for commercial applications like giant football stadiums or a university gym or something. And then concluding remarks. I guess the important thing to take away from this is that just because it's the cheapest material doesn't mean it's the best option. It really depends on a lot of other factors.
Hello, my name is Nick Royal. I did my design on materials for flywheels. So choosing materials for flywheels, there's actually 2 scenarios that were looked at in this case study to create the most efficient flywheel. So the first is, I guess, your more traditional flywheel where you want to maximize the energy stored in this wheel as it's spinning per the unit weight of the flywheel. Whereas the second is for a child's toy. So, the child has a limit to how fast they can make the wheel actually spin. It's never going to reach a velocity where the wheel would break. So in the first scenario, we're constrained by when the flywheel will actually break and reach its tensile strength. In the second one, we're just looking for the maximizing the energy per unit volume, since the child's never going to reach a velocity that's too high for the flywheel to handle. So in both scenarios, we started with energy and came up with a similar equation. In the first scenario, like I said, we're doing it per unit weight or per mass. So we end up getting a material indice with the stress over the density. We want to maximize that in order to get the most energy per unit mass out of the flywheel. In the second scenario with the children's toy, the only variable that we have to play with is the density, since the radius of the flywheel is fixed and the angular speed is not going to be variable, since we're looking at the maximum that the child can do. So we get two lines on our material chart. For the first scenario, we're looking up in the top left corner, and in that region we get the best material choices of the carbon fiber reinforced polymer and some high strength titanium alloys that are able to withstand that tensile stress and give you the lightest option. And the second, with the children's toy, we're just, like I said, looking at the density of the material, so that's the vertical line. And then we want anything to the right of that. And these lines were picked based on a kilojoule per kilogram value of 200. So using that as your ideal, looking in the regions beyond that. So lead actually comes out to be one of the better options, which kind of surprising.
That's what I thought, right?
Right. So maybe it's in, you know, part of the toy that the kid doesn't touch. I don't really know. Maybe not ideal, but other options over there, you're looking at the heavier metals. So cast iron was one of them as well, although the case study insisted lead was great. I can't really speak to that myself. I wouldn't choose lead personally. But looking at the key takeaways from it, so again, it all depends on what the application of the design is for, whether you want to maximize the energy per mass or try to get the lightest for a child's toy or the strongest for a child's toy. The materials for the first scenario, carbon fiber is probably the best option, or the high strength titanium alloys. Again, they insisted lead, but cast iron comes in a close second. It's just not as cheap, because you want, and then you wanted the high stress to density ratio and high density for the second scenario. The main limiting factor for the different materials you can choose from with the first scenario, some ceramics also fell in that range, but they aren't tough enough to withstand the forces needed. And then it was mainly practicality for the children's toy. So